Okay, let's talk some more about functions. So we saw in the last video that this is not a function, and the problem is that we don't know what f of 1 is. So the uniqueness condition on a function says that for every x in the domain, it must have a unique y in the codomain. So if you ask yourself, what is f of x, and you know there's only one answer for every x, then f satisfies the uniqueness condition. Now, the way I drew this is not a function either because I don't have values for the rest of the a's in the domain. But this is where it's failing the uniqueness condition. Let's look back at this example. This example we said is a function. Notice, first of all the elements in the domain are mapping to something in the codomain. But we have this issue right here where I have two different x's mapping to the same y. That's perfectly fine. Okay, this is still a function because if I ask you what is f of 1, you say it's a. And if I say what is f of 2, you say it's a. So every x in the domain A has a unique value y such that f of x is equal to y. So this is a function. What's going on here? So I'm asking you right now, what's going on here? What's the problem with this function right here? It's not necessarily a problem, but it's something that maybe you don't like. And the answer is, this function f is not one-to-one. So let's go ahead and define what we mean by one-to-one, which the book calls injective. So we'll use both of those names interchangeably. Injective, and then the other one that you probably know is onto. So this function right here, as I've drawn it, is neither one-to-one nor onto. So let's go and define what we mean by one-to-one and onto. If you're following along in the notes that I posted, quick note about those notes. Those are my notes, the ones that I carry with me to class, and I use when I write stuff on the board. They're not perfect. They were not meant to be copied and distributed. However, when they said we're shutting down JMU, I quickly scanned all of my notes, and there you go. So use those if you want, but the recorded lectures are going to be a better set of notes. So in my notes, I have a couple of examples of functions. I'm not going to spend time writing those out in these notes. Look at them in the scanned notes, and you can also look at them in the text to get some more examples. So let's talk about these properties of one-to-one and onto, or injective and surjective. So let's go ahead and let f from a to b be a function. Notice how I write that. A is the domain, b is the codomain. If f is a function, then I know it satisfies the two properties where every element in the domain gets mapped to an element in the codomain, that's existence, and every element in A gets mapped to a unique element in B, just like we talked about. Okay, so another property that a function might have, it doesn't need to have, is called one-to-one. So f is one-to-one or injective. Okay, these are two words for the same thing. If for every element B in the image of f, okay, not just for every B in B, but for every B in the image of f, there exists a unique A in A such that f of A is equal to B. So let's go back to the other example and look at it using this definition. So f is injective if for every element in the image there exists a unique element in the domain that maps to it. All right, here we go. All right, there is the example from last time. This one's not a function, so we're not even going to look at this. we start off, it has to be a function first. Okay, so this definition is only for functions. Let me slide this down just a little bit. Okay, so it is a function. So what we're saying is that every element in the image, okay, here's the image. I don't care about these elements out here, B, G, and F. Those are not in the image. They don't have to have a unique element in A that maps to it because nothing maps to it. So we look at the elements in the image that have an element that maps to it. And we want to say, does each one have a unique A that maps to it? Well, E does, yes. 5 maps to E. C does. 3 maps to C. Nope. 4 maps to C. D does. 3 maps to D. But notice A does not have a unique element. Both 1 and 2 map to A. So this function does not meet the definition for one-to-one because there exists an element in the image that does not have a unique element in A that maps to it. By the way, these elements over here are called pre-images. A is the image of 2, and 2 is the pre-image of A. Okay, so hopefully you understand the idea behind one-to-one. And I'm going to say that this definition is for understanding. So hopefully you understand it. I'm going to say right now, this is not a good definition for proofs. And since that's what we're doing mostly in this class, I'm going to give you another definition. Okay, so here's another definition. So F is one-to-one or injective if, here we go, if f of x equals f of y, then x is equal to y. Okay, and in my notes I say this one is for proofs. Okay, let's go back and look at the example and look at this definition. So this definition is for proofs. It's not as easy to understand. Okay, the first one is very good for understanding. The second one is equivalent, but it's not as easy to understand. Looking at the example will help though. Here we go. I'm going to put the other page in. Right. Okay, here's the example. The definition says if f of x is equal to f of y, then x equals y. So here we go. Here's an example where I have an f of x, where x is 1, is equal to a, and I have an f of y, where y is 2, is also equal to a. So I've got an f of x is equal to an f of y. But yet, x is not equal to y. So this function is not one-to-one, because I've got an f of x equal to an f of y, but x is not equal to y. And we'll do some examples of proofs where we use this definition. I'm also going to give you a boilerplate for how to prove a function is one-to-one, and we will use that second definition. One more definition that's basically the same as this one. You can also use it for proofs. Sometimes, as you know, for proofs we need to use an indirect proof or a proof by contrapositive. So here's another proof. F is one-to-one or injective if, now I'm just going to do the contrapositive of this. So if x is not equal to y, then f of x is not equal to f of y. And you can just look back and see. And of course, if you believe the one above it, you should believe this. So to summarize the injective definitions, we've got the first one here is a great definition for understanding what one-to-one means. The second definition is good for using in proofs. And the third definition you'd also use in proofs, but only when you can't use number 2. So these are the 3 definitions. They're all equivalent. Really just 1 and 2 are different. So if I ask you on a quiz, give me 2 definitions, of injective, you would want to use definition 1 and definition 2. Okay, let's talk about surjective or onto. So here we go. Definition. Let f be a function. Then f is onto or surjective. Notice the sur for on. Surjective. If. All right, let's do two definitions once again. It will be onto if for all elements in the codomain there exists an element A in the domain such that f of A equals B. Right? Notice there's no uniqueness condition here. And really what that is saying is that the image of f is just equal to the codomain of f. All right, so this one's good for understanding. The image is just equal to the codomain. Whoops, I'm off the page. Sorry. The image is equal to the codomain, and then this one is what we're going to use for the proofs. For every B in B, there exists an A such that f of A equals B. Let's do a quick diagram for this one. Here's your domain. Here's your codomain. Have your function f, and let's say put some elements there in A, and let's put some elements here in B. And if the image of f is everything, so there's nothing left outside there. If the image is everything that's hit by the elements in A, then it is onto. So let's draw our little arrows here. Did everybody get hit? No, this one needs to be hit. And that one still needs one. I'm just going to make that up. There we go. All right, there we go. Now the image is all of the codomain. So this function is onto. Okay, finishing up this section. Last definition, a function is bijective or a one-to-one correspondence if the function is both one-to-one and onto. That's an easy definition. Bijective is definitely more common than one-to-one correspondence, even if you're using one-to-one and onto as your definitions. Now the last thing I want to show you is how similar these definitions are. So many students get confused about the difference between the definition of function and one-to-one, and here's why. So the definition of function is we've got f from A to B, right? So we've got a domain and a codomain. Definition of function is for all A in A, there exists a unique B in B such that f of A equals B. Okay? Definition for one-to-one, for all B in the image of f, there exists a unique A in A such that f of A is equal to B. And before I talk about the differences, look at onto. Onto is for all B in B, doesn't have to be in the image, there exists, not unique, but there exists an A in A such that f of A is equal to B. No wonder students get these confused. They are almost identical. One thing I'm going to point out here is notice function starts in A and goes to B. We say that's a forward condition. We go from A to B. Both one-to-one and onto are backwards conditions. You start with something in the codomain and you show there exists something in the domain for both of these. Okay, so function is a forward condition and one-to-one and onto are both backwards conditions. These two, function and one-to-one, are very, very similar. The whole structure is set up the same, except that I've reversed the A and the B, right? And on this one, it's